Hi everyone. We are starting live now with our webinar, Hopsworks webinar, the first of the year. So welcome for those who are coming in. Today we're going to talk about models and futures better together. And we have two speakers tonight. We have Jim Dowling, our CEO, and we have Javier, who is a software developer of the Hopsworks platform. Thank you both for coming. Just a few reminders before we get started. We will have a Q&A at the end of the webinar, so please send your questions using the Q&A button at the bottom. This helps us make sure that we get to see your answer, because if you send it on the chat, we're going to see a lot of message there. And we are recording the webinar, so everyone will receive the video recording at the end. Without delay, I'll pass it on to Jim.
Thanks, Natalia. Okay, so hi, I'm Jim. I'm going to share my screen. We'll get started. You can ask questions with the Q&A button. So the Q&A button, and I'll try and answer them if I see them while I'm talking. I'm going to kick it off, and I'm going to talk about Hopsworks and model management and the feature store. And Javier will do a demo towards the end. So shoot with your questions. We'll try and take them as we go. Let's get started. So this is the obligatory sign. Why you're working with AI, I assume, or machine learning. What kind of problems do you have? This is quite a good read. Generally, these things I find a bit dry, but O'Reilly had a publication earlier last year about the challenges people have in adoption of AI. And many of the challenges are really that you don't know what to do. So maybe you don't have data, good enough data. Maybe you don't have the business use cases that you need. Maybe your company culture doesn't need it. You really need to work in your data. You need to get started with data before you really start doing machine learning. But then you get technical challenges as you have some form of data process in place and some sort of data plan. And you get then higher challenges. And we can see small things like model tuning are not huge problems for a lot of organizations. So how do we see the version of this journey that companies make to being AI enabled, to building AI enabled products? So if you think about it in terms of your machine learning capabilities as an enterprise, and we start from here and move forwards on the x-axis, you can think that first you need to have control of your data. So you should have some management of your data in place. Maybe you'll have a data warehouse or a data lake, and you'll be able to make some insights in that data, some historical insights with business intelligence software, and that will generate quite a lot of business value for you. And you might start with data science by doing reports, so doing predictive models and generating reports. We call that artisan ML. But then when you want to actually generate services that make predictions and generate value, we move up into batch machine learning, where we can do reports with machine learning predictions, to real time. And that's the focus of today. We're going to talk mostly about real-time prediction, either with historical data or with very fresh data or streaming data. It doesn't really matter for the purposes of today, but the main point is that you have a service that you're providing 24/7, an online service. It's going to make predictions, and it's going to use a model and the feature store to help make those predictions. Excuse me. So a little bit about us. We're Hopsworks. We make Hopsworks platform. It's an open source, data intensive AI platform, and it has the most advanced feature store out there. We have a bunch of companies who work with us and use our feature store and our platform. And here's a number of them. I'll skip over that quickly. And Hopsworks is an open modular feature store. It's a standalone feature store if you want to use it that way. And many of our customers are doing that. So if you have your data in Snowflake or Redshift or in a data lake, and you want to get it into the feature store, we support that. We support Python, Spark, and SQL as ways of computing your features. So computing aggregates of your data and writing them to the feature store as features, and even Airflow and other workflow orchestration tools. So we also support are making the features in the feature store available as training data for data scientists. So in their data science platform of choice. So if you're working with SageMaker or Databricks or Azure Machine Learning Studio, you can produce training data in S3, for example, or an ADLS, and then your data science platform can read that training data, train models, and deploy a model to model serving infrastructure. And again, there's many choices out there today. You have managed platforms such as Azure Machine Learning Studio, SageMaker, Databricks recently released one. There's open source, and we'll talk about Kubeflow's open source framework primarily today. And Selden is also a good open source and enterprise option. And then finally, you have data discovery and compliance platforms that can also integrate with our platform. So all these platforms can integrate with our platform and use it as a standalone feature store, and that's great. The platform is available on you can install on any platform. So we have a managed version on AWS and Azure today, GCP coming soon, or you can install it on any Linux machine, so Red Hat or Ubuntu. Now, the problem and the challenges, I think, of plugging together all of these systems, if you have a data engineering setup, you have a data science setup, you have model serving, and you have data engineers, machine learning engineers for serving, and you have data scientists for training models, is putting all this together, right? Because we have this external forcing factor that's changing the industry. There are regulations that are coming to AI, and they're coming soon. And what you have to do is ensure that the models that you put in production follow these 5 established principles, so that your data sets are relevant, representative, free of errors, and the feature store will help you with that. Provenance and traceability of decisions becomes very problematic when you go from one system to another, from your data warehouse to the feature store, to the machine learning platform, to the model serving platform. And as we have the same problem with understanding and controlling the AI system. So jumping between systems is an issue. So cobbling together many platforms is going to make it hard for you to meet these looming regulations for AI. There's going to be more convergence on platforms that provide more capabilities for you. So that's what we're going to talk about primarily today. And we're going to not just talk about the Hopsworks feature store, we're going to talk about the support for model serving and its tight integration with the feature store. So it's an operational platform, Hopsworks, for features and models. Now, we've had this capability for a couple of versions of the platform. So we've had support for Kubeflow model serving since 2.3, I believe. But that's been for people working inside the platform. So if you're doing your model training inside Hopsworks, yes, it works. But what if you don't use Hopsworks for your model training? Maybe you're using SageMaker or using laptops or notebooks, or maybe you have a GPU server under your desk. Well, that's what we're going to talk about today. So we're extending the platform to make it so that you can use the feature store from any external Python or Spark client. And the same will be true for model serving in a very new release coming soon. So the platform will manage the features, and the features will be available online and offline. I'm not going to talk too much about the feature store today. There'll be more emphasis on model serving. And the model serving part, we're going to talk about KServe primarily. We'll look a little bit at model monitoring, the model repository for managing features and for managing models for KServe. So we have a model registry that's designed specifically for KServe. And we'll talk a little bit about how we put the pipelines together to train models if you're using your own data science platform. So for people who are maybe training on your laptop or on desktops or on virtual machines in the cloud. Okay, let's get cracking. So just going to start with a little bit of background so that we're all on the same page, what we mean by an operational AI platform. So you do have batch models, so models that are used to make predictions. And earlier I showed this, we can jump back a little bit to see what I mean. Earlier we looked at this particular curve. We said we have batch ML, so batch machine learning, and we can go up to create more business value with real-time machine learning, real-time prediction. So batch ML is a way of maybe building a service, and the service might make predictions once per day. Maybe we're going to take in all of the orders that arrived yesterday, and we're going to run a batch application. We'll make predictions about what stock we need to purchase to ensure that we don't run out of stock of items that were ordered the previous day. And it'll generate a report somewhere, and somebody can use that report then to maybe purchase enough stock so that the system the e-commerce system is fully stocked. And that adds business value, sure, but operational models are more about user-facing models. It's about services and applications that run 24/7. So maybe you have a customer-facing retail application and you'd like to build a recommender system to recommend particular products for them to buy. So then you'll need to have models that run 24/7 on model serving infrastructure. So if we take these operational applications and start at the user is using an application, and the idea is that this e-commerce website, for example, we're going to make it more intelligent by adding recommendations to it. So personalized recommendations, maybe personalized search as well. So to do that, we need to train a model to help make good recommendations. So the model is going to run a model serving infrastructure, but that model is not enough by itself. It'll need history and context. It'll need to know, what did you buy in maybe the last hour or the last week? During this session, what pages did you visit? Context, so what's popular right now? What are other people buying who bought items similar to you? The model itself needs to come from a model registry as well. And the feature store by itself is not just some static database with a dump of data. It needs to be updated all the time. So it needs to connect to your back-end enterprise data systems to keep updating every time you buy new items, every time you maybe visit new pages. We need that data to be constantly updated and kept fresh in the feature store so that the models can make the predictions on the freshest data. So latency and availability of operation models is crucial. And the main thing to note just from a high level here is that operational models are complex. Compared to the batch models on the left, you can see they're operationally much simpler, and the operational models need a lot of infrastructure. So if you're going to go down the route of operational models, you need to invest in infrastructure. And that's what we're going to talk about, how Hopsworks can help meet a lot of these requirements. So you hear a lot about MLOps, so automated training of models, automated computing of features. Automation and testing are the real key components or ingredients in MLOps, that your models can be maybe automatically trained when new data arrives, or that new features can be created automatically when new data arrives, and we test to make sure everything's good before we deploy new features or before we deploy new models. Now, the analogy I like to use here, because we're Hopsworks, and some people, for whatever reason, confuse us with beer. I have no idea why, but if you consider a model as a beer, it's nice to have one beer, that's great, but a beer in its own is just a one-off thing. You don't get value of it from it over a long period of time. A brewery that makes beer the whole time and a pub that serves beer the whole time, that's value. So if we think of this analogy of what is MLOps from a Hopsworks perspective, you can think of data being the original ingredient coming into our brewery. So this is the source of the data. We get features are generated from that data, and we get training data from the features, because we want to be able to reuse those features across many different models. So each model might have its own training data set. We then need to actually train the model. So we're going to brew in here in our brewery, and we're going to spit out our model into this nice cup. So you can think of the brewing process here as being the offline feature store. It's managing the data for the models, so the machine learning models, for creating training data to train models with. You need an ML platform to train models. Today we're going to talk about external platforms for training models, but Hopsworks also has its own model training infrastructure. And then the model itself is no good by itself. So if you just have a model and you're taking in requests, we know that it needs to be connected to a feature store to give it, an online feature store to give it history and context, to be able to say, okay, well, what has the user done in the recent past? What is popular right now? I need that information to build my feature vectors that could send to the model for prediction. So, and the model itself will typically run behind some endpoints, some network endpoints, so that you can make requests to it. And they would like to be secured and scalable, so load balanced over many model instances. That's why you need model serving infrastructure. So this is kind of the whole MLOps from a Hopsworks perspective. It's not the beer, it's the services that make the beer, the brewery and the pub all together gives you the whole experience. And that's an analogy, by the way. So let's get look a bit in detail at KServe. For those of you who aren't aware of KServe, KServe is effectively the de facto open source model serving framework for Kubernetes. And it came from a project called Kubeflow, many of you will have heard of. So Kubeflow is a machine learning project for training models, for serving models. It was released by Google maybe 3 or 4 years ago. And Kubeflow needed a model serving component, so they introduced KServe. Now, Selden had the first version, but then Google rewrote some of that and released it as KServe. And there's a few other companies like Bloomberg and IBM who are very active in the project. So one of the problems that's happened with Kubeflow is that Google have pretty much abandoned this because their focus is now on their managed platform Vertex. And that meant that KServe, which has been one of the very successful projects within Kubeflow, decided to go alone. They didn't want to be tied down by Kubeflow, so they've started as their own top-level project at the LNCF. So KServe is now the name of what was previously KF Serving. And KServe is a model inferencing platform that runs on Kubernetes. And you can see the stack on the left-hand side. So you have Kubernetes managing your resources, so GPUs or CPUs. KServe builds on top of a framework called Knative, which gives you scale to zero, or the ability, if you have a model running that's not taking requests, that it can free up its resources and allow other models to use its resources. So resources in this case would be CPU and memory. So we think of it as being a serverless layer for Kubernetes. And then we also have Istio as a layer here. So Istio gives you authentication, access control, and routing. So we actually do access control through Hopsworks, but authentication we'll use through Istio. And then Istio can also do load balancing across many instances of your models, and it will do the routing for you. KServe also supports multi-model serving. So one challenge that you have if you use a managed platform is you develop a model and say, please deploy model, and you get a container, or you get a virtual machine, depending on the platform you're running on. And that can be quite expensive if you're going to start running hundreds or even thousands of models. So multi-model serving is the capability to run multiple models inside the same container. So that in combination with the serverless layer Knative means that KServe is ideally designed to run with very large model serving, I guess, forests of models that are running in the same cluster. Other capabilities that you have are A/B testing of models. You can deploy them and see how they're performing before you promote them to being from a challenger to being the main deployed model. There's also support for transforming the inputs before they get actually sent to the predictor and explaining the predictions that are made. You can also have complex, what we call inference graphs, where the output of one model is the input to another model. So maybe some model is predicting stock and another model is predicting what the best place to fulfill that stock should be. And then you get then an output, an order is made to fill up the stock. And then finally, a new capability in KServe is something called model mesh, which I'll talk about in the next slide. So model mesh is a new framework introduced by IBM into KServe, and it just came in at the end of last year. It's really think of it as being kind of, it's almost like if you go back to J2EE, where you could deploy many Java applications on the same J2EE cluster. Now you can deploy as many models as you like on shared resources without needing to actually encapsulate them inside a container. And they've shown incredible scalability. So on even 4 servers, they could host thousands of models in parallel. It's not quite as mature. There's some things missing. Transformers are not there yet, but it'll get there, they promise, by around Q2. So there is a Grpc API for model mesh. They're adding REST support with a gateway, but KServe, the original KServe, this KServe controller at the bottom here, supports both Grpc and REST API endpoints for making requests on. So what KServe looks like inside a pod, we'll have a serving container which has the predictor. We have a predictor component. You can have sidecars in here. We use sidecars to log the prediction request back to Hopsworks. And you can have a puller as well that's going to download artifacts that are needed. So you can have it from a persistent volume plane, but then we also have then the operating system that the containers run on. So KServe is great. It's probably the most advanced model serving framework out there from all the open source ones at least. And it has incredible capabilities that help you run production models, production models that you're serving to large numbers of applications. Now, you do need more than just KServe actually to run intelligent applications, because the models themselves and KServe will also need a model registry where the models are hosted. So we'll talk about that today. We have a model registry in Hopsworks that's customized for KServe. You'll also need to be able to call the feature store to build the feature vectors. So when a request comes into a model, the application may not have all of the knowledge it needs. It may not know the history of your interactions with this e-commerce retailing platform. It may not know how much you've spent in the last month. It may not know how many pages you visited on this session, but it can go to the feature store and look that up with your user ID. So that's what happens in your transformer. In KServe, we're able to actually integrate with the feature store, pull out the features that are needed to build our feature vectors, and then send them to the model for prediction. So when you've model serving infrastructure that's generating predictions, it's generating a log of these feature values, the predictions that were made, and then also at some point maybe the outcome will become available of the prediction. And that may not be within your model serving infrastructure, it may be somewhere else, But you would like to have all of the predictions that are made, all of the features values for all those predictions logged back to the feature store so that we could generate new training data. Because if you're running a model against customers live and it's making predictions, and you know the outcome of those predictions at a later point in time, that's gold. That data will help you make better models, which will give you more intelligent applications. And then, of course, developers need to be able to manage models. So stop them running, register them with the model registry, delete them, and also deploy the models to endpoints in KServe. And you can, of course, teach your data scientists to be Kubernetes experts. But what we're trying to do is abstract away as much of that complexity as possible so that ordinary data scientists don't have to learn the innards of Kubernetes to deploy models to production. Obviously, there will be in large organizations an ML engineering setup that will do this, but really the goal here is to simplify as much as possible. Okay, let's jump into Hopsworks and have a look at the platform. So Hopsworks, it supports ingesting data from different sources, computing features. You can do that outside the platform, of course. We have the feature store, model inference and monitoring, and registry, and then management and governance of the whole platform. So all the capabilities you need for operational machine learning platform, training and development, you can do, of course, outside the platform, and we're not going to talk about it too much today. So there's quite a lot on this slide, and I'm not going to go through it in too much detail. But basically, your data is going to come in from an unstructured, a structured data source. You might have a connector to a data warehouse or a data lake. You're going to pull that data in either with batch applications or streaming applications. So for very low latency data, very fresh features you need to push in, maybe it's a streaming app, but in the common case, it'll be a batch application run on a schedule. And that data will be put into what we call the offline feature store. The historical feature values that we use to generate training data will be stored there. And in our case, this is going to be S3 and hoodie tables in the cloud. And in the online feature store, we have our own database, RonDB, which gives you very low latency and very high throughput performance. It's an in-memory database that we develop primarily for this use case. And then there's a lot of other features around the platform. You can run compute inside the platform, or you can run it outside. And we do have support for data validation, statistics, compute over features, and the model monitoring that we'll look at in a second. Okay, so why are we doing this? Why are we integrating a feature store and model serving? Well, the main motivation for this is to enable people to build a data for AI flywheel. That means that, okay, you're going to use a feature store to manage your data. You're going to use the model serving infrastructure to provide model prediction services to applications. But really, we want to also collect all of the data. So as more users come to your platform, they're going to generate more prediction requests by using the services. And you're going to find out the outcomes of many of those prediction requests. And you're going to have more data with which to train better models, which will give you better predictions. And when you have better predictions, your product will be better. So any data-enabled product will become better. And a better product will attract more users. And that's why we call this the data for AI flywheel. I'm not the first to come up with this idea. Several people have talked about it before. But this is what we want to enable, that by having systems that collect data and reprocess it to make it available to train more models, you'll get increasingly better applications and better predictive models. So how does that translate into practical systems? Well, if you're serving your models on KServe and it's sending its prediction logs to Kafka on our platform, we log those predictions and the outcomes if you can push them into our platform. You'll have to do a little bit of work there because the outcomes, as we said, can be, did you buy this item or not? So you might have to then push that to a different topic in Kafka that the item was bought, or we can use a timeout to say it wasn't bought. And then we'll have training data, new training data in the feature store. And with that training data, you'll be able to retrain better models and then redeploy them to KServe. So this is the data for AI flywheel that we want to enable with the tight and seamless integration of KServe and the Hopsworks feature store. So if you're to take a slightly bigger picture, a more practical system, well, I have a website. It has users. That website is going to log the predictions that are made. So those predictions get logged maybe to our platform, maybe to a data warehouse, or to Kafka, and then we're going to have to do maybe some feature engineering on them before we put them in the feature store. And the feature store will give this online API to the model serving infrastructure, but it will also enable you to create training data, and training data will be versioned just like the features themselves, and the models will be versioned in the model registry. They'll be deployed. And this is the same data for AI flywheel, but in the context of maybe an online web application that someone is using. And then you have set up ML ops, so automated pipelines to make sure all of this happens in an automated and tested and controlled manner. Okay, let's look at the model registry as a starting point. So the model registry we've developed, you can see it on the left-hand side here, and Javi will do a brief demo of it later. We have a library called HSML for accessing it. It's a Python library, and we also have REST APIs. You can deploy a model from here, from the user interface if you want, instead of from code. What's interesting and what's unique to KServe is that we have not just models, but models can have artifacts, so libraries that they need to do something. And we version both the models and the artifacts in our model registry. So if the model stays the same, for example, but the libraries they're using change, you get a new version for the artifacts, and you can deploy those separately to the model. KServe supports multi-model serving, so our platform is aware of that. If your model here is being used in many different serving instances or deployments, and if it's being used in deployment that has many models, you can be aware of that from here. And also, the feature store will generate your training data, so you'll be able to see the provenance of models, what training data was used to create this particular model, even if you train the model outside the platform. So how do we use this Hopsworks KServe setup if let's say I'm using SageMaker, or I'm using my laptop or some desktop machine? Your training pipeline is going to look like the following. Firstly, you use the feature store to create your training data. And we have an API called HSFS for that. With your training data, if it's small enough, it can fit in memory in a pandas data frame. Otherwise, you can store it as files, so CSV files or TF record files if you're using TensorFlow, and you can read them up and train your model. So when you've trained your model, again, we use this HSML API, Hopsworks Machine Learning API, to register the model with our model registry. You would then like to evaluate your model, make sure that it's working as expected. So one way of doing that is to evaluate it on different slices of data. Because of regulation, we need to show that our models don't have bias against people. So often if you have a consumer-facing app, you might decide to evaluate your model against different genders, for example, and make sure that the performance of the model is comparable across the different gender groups. And then you can generate reports based on that, or have tests that you would like it to pass if you're doing MLOps. And then finally, you'll need to deploy your model if you're happy with that it's passed all the tests and its performance is better than the existing model running in production. And you would like to do that by A/B testing to begin with the challenger response model, and then finally promoting the model if it's good enough. So what you can see at the bottom is Hopsworks provides the infrastructure for which you can do all this, and the top can be done on anything from a data science platform to a laptop. So let's look at this library. So this is new for this webinar. We haven't talked about this new library, HSML, or Hopsworks Machine Learning API. The HSFS, the Hopsworks Feature Store API, we've talked about before. So you can pip install it from any Python client. It will give you access to the model registry and model serving services in Hopsworks. And if you want to use a feature store, you can use the HSFS API. We're actually pulling this all together for a single API, but that's not ready today yet. Now we have currently 2 dedicated APIs, which is great if you're just using the feature store. You only need the HSFS API. So let's look at creating training data. I'm not going to spend too much time on the slide because there's quite a lot of code in it. We can see that we're using the HSFS API to connect to our platform. And you can run this from any Python client, for example, and then you want to get what we call groups of features. So in our feature store, we organize features in tables or groups. And we've got one table or feature group called rain, another one called temperature, another one called location, and they all have features in them. And what we want to do is pick some features and join them together from these different tables to create some training data. So that's how we reuse our features across different models, that these feature groups are reusable and they're also updated the whole time. Training data, on the other hand, is typically immutable. You just create it once and you train one model on it typically, and then it's done. So here we have, you can see we have a very simple DSL for joining features together. You can say select all the features in the rain feature group, join them with all of the features on this temperature feature group on date and location ID. So the query planner will look for a common join key between feature groups, and that join key will be part of the primary key. You can have a multi-part primary key. In this case, it would join on locations. What we're actually trying to do is create a training data set to look at the rain in a particular location. So we get the amount of rainfall or precipitation in that location, the temperature in that location, and then features related to the location itself. Maybe it's altitude, or maybe it's how prominent it is. And we can also, in this DSL, we can also have filters, things like as of, I want the data as of this point in time. So all the training data after that particular date I would like to retrieve. So with this object, we can create a training data, a feature join object, we can create a training data set. And we're saving that query object into that. We can also get a pandas data frame with the train data directly from the feature join object. But in this case, we're actually saving the train data as TF record, and we're splitting it automatically. So we got some training data, great. Now we can train a model. And I don't show the code for training the model. We're just kind of, that you've seen it all before. But what's interesting is how we're using the HSML library here to register that model with the model registry. So again, the same as HSFS, we need to connect to the model registry. Then we can create our model. We can put in whatever metrics we want in a dict. So we have a Python dict in here, and they will become available in the model registry. So you control what metrics to show, and you can have a description. And then we basically need the path to the model that you've saved. So in TensorFlow or in scikit-learn, you will have saved your model to a local directory, and then we're going to write that to the model registry. We'll upload the model's pickled Python file if it's scikit-learn, or the protocol buffer file, and weights in TensorFlow. Now, the third step was evaluating your models. Now, I don't have any code to show up because the code actually is quite involved here, but it's easier, I think, to understand it from this higher level perspective. And what you want to do is have automated tests to check to make sure your model works as expected. So you're going to train your model, and you're going to have a pipeline that will run maybe unit tests on some parts of if you're doing feature engineering in this model training step. You might have an end-to-end test, which is just making sure that the model gets trained and written to the model registry as expected. But the model validation tests will typically, we want to use them against slices of test data from your model. So you have your holdout data, and maybe we slice it by gender. So then we can compute the accuracy of the model on the 3 different genders, and make sure they're all close enough to one another. And if they're statistically significantly different, then you can fail that test, as an example. And this translates. So if I do this on my laptop, and I will need a connection to this Hopsworks development project with my development model registry. But I've run this code on my laptop and it's passed all the tests, and I'm happy with it. What I can do is I can just trigger a pull request on our main branch, and then that will trigger the same pipeline and run PyTest over it to ensure that this model then gets written to the staging model repository registry. And if it doesn't pass the test, of course, you have to go and fix it and then re-trigger your Jenkins pipeline. So we've trained our models, we've ensured it passed all our tests, and now we want to deploy it to KServe. So again, we can use HSFS. There's different ways you can find your model. You can go to the model registry and say, give me the one that has the max accuracy. So we have a model called rainfall, we have a metric called accuracy, and then we have max min. So we can say the max of this metric called accuracy. And we get the model with the highest accuracy, and we deploy that. You can also say, well, just give me the version of the model. And obviously, in many cases, if you have compliance issues, you want to make sure that somebody maybe ticks a box or ensures that they're authorized to deploy this model before it actually gets deployed to production. So let's jump into the internals of KServe, and we'll have a quick look at it. So KServe, remember, the model is being served. So the model is down here in the predictor. So your model is going to be inside this predictor class here. So you have an object here. You can have a transformer. You don't have to have one, but you can have this transformer, which will take the input. The input comes from over here. The input comes in, let's say, to the default endpoint. The transformer can do some transformations on the input before it passes over to the predictor. We'll see that we'll use a transformer to actually go to the feature store to retrieve features. To the explainer component, I'm not going to go through today, but if you aren't training deep learning models, if they're, let's say, gradient boosted decision trees or just decision trees, You can use feature importance algorithms to explain why the prediction was made the way it was. And there's SHAP values as well that you could use. But this is, again, you roll your own. So you write one of these per model that you deploy. And then, as I said, A/B testing is supported. So when predictions come in, they can be sent to different endpoints. So you might have 95% of the traffic going to the default one and 5% to the new canary. So you can see you can call predictor explain, and predict. There's also you can have classify or regression endpoints that you on your predictor that you can have in here. So this is KServe and what gives you out of the box. So what do we add in Hopsworks? So what we add is the ability to have a transformer that goes to the feature store and builds the feature vectors for you before they get sent to the predictor, which is great, because then you don't have to worry about all of the complexity of writing transformation functions here and ensuring they're consistent with the transformation functions in training. What we also do is we'll take the predictions made by the predictor, and also even you can have other points that you would like to log. You might want to log the raw data coming in or the transformed feature vectors before it's sent to predictor. We have a sidecar that can send these inference logs to Kafka running on our platform. And then you can have a Spark application that you do have to write, and that can write these inference logs to the feature store. It can also do monitoring as well. So you can look for things like drift and outliers. And you can also, of course, then look for outcomes and try and write them to the feature store. And this is really closing the data AI flywheel, as we talked about earlier. So let's look at that in a little bit more detail. So how do we plug in the transformer to the feature store? Well, we can see here we have an application out here, and the application is sending a prediction request, step number 1, to KServe. What KServe has internally, we know it has this transformer, and the transformer receives the prediction request first, and it's going to send it on to the predictor. So the transformer, what it will do is it will send, we can see that it says request features here. This is transformer code we can see here. It receives the inputs here, and it then basically says, go to the feature store with this TD object, and here's my input. The input that came in arrived in at number 1, the credit card number. With that credit card number, we can look up a lot of features related to that credit card. So the feature store will return those features. It will actually apply transformations. If you've defined transformations on some of those values, we can actually apply what we call online transformation functions written in Python inside the client here. So you'll get back the Python array or the tensor, depending on what type of your model is, in the correct format, and then it gets sent on directly to the model, the prediction endpoint, to make the prediction. You can see there's an initialization step to the transformer as well. So rather than have to set up a connection to the feature store every time a request comes in to the transformer, we can set that up when the transformer starts so that it has a persistent connection to the online feature store. So so this is step 3, where the feature store returns the enriched feature vector with all of the features we added to the credit card number. And that Python, or it could be a NumPy array that's returned, and it's sent to the scikit-learn model to make the prediction, and then the result is finally returned to the application of the prediction. So that's plugging the transformer in KServe into the feature store. The other thing we need to do is we want to take these inference logs and maybe we want to use them to monitor the performance of your models. So we actually have a nice Spark application that you can customize, which computes outliers and drift on feature values. What it does is it uses the statistics of your training data in the feature store. So it actually goes to the feature store. It'll get back the statistics that are computed over all the features of the training data set. So descriptive statistics are pretty useful. And then with those, like min-max, it can find outliers. And you can compute drift with we have a couple of custom applications or implementations of data drift in there. You can, of course, write your own as well. So how do we put this all together, right? So I've kind of presented a big picture of the feature store, and your model serving infrastructure should be as tightly integrated as possible so that you can get the benefits of data flowing into the model serving layer being fed back into the feature store and getting the data AI flywheel going. I'll just show you a very complex example that we're working with right now, which is what we call retrieving and ranking architecture. And this can scale to millions of operations per second on our platform. But what it's used for primarily is for personalized search and recommendations. And it's the state of the art in personalized search recommendations. It's called a two-tier embedding model. And it has a retrieval step and it has a ranking step. So what happens is we have this person up here is watching maybe a video, and they finish watching the video, and the streaming system is going to recommend the next video to watch. So what it's going to do is it's going to look up the user's history of what they've watched, the particular movie they've just finished watching now, maybe features of that movie itself. And with these features, we'll compute something called an embedding. So this embedding will be called the user embedding, let's call it the query embedding or user embedding. And with that embedding, an embedding is just an array of floats. It's just a vector of numbers. We actually can go to something called an embedding store to say, give me the 200 closest movies to this user's input vector or feature vector. So this is going to give us 200 or maybe 300 or 500 potential candidates of videos to show the user. It's quite a lot. We're not going to be able to show 500 candidates. So what you can do is you can take the movies that have been returned and enrich them with features. So the movies, we can get what genre it is, how long does it take to what the running time, and so on. And then you can use a faster model called a ranking model to rank those candidates. So we'll go from several hundred candidates here, which may not be very diverse, which may, maybe the closest ones in the embedding store are very similar, but we want to have a more diverse ranking, and we want to have fresh videos we want to show diverse and so on. So the ranking can take all of these into account and send the candidates back to the user. And you want to do all of this in less than 100 milliseconds. So this is where we have the exact same infrastructure we talked about. We have a feature store to help build the embeddings for looking up the closest movies in something called an embedding store. Our platform also has OpenSearch, which has an embedding store. So this is coming out in the next version. OpenSearch has a plugin called KNN, which gives you an embedding store. And then the candidates returned, we go back to the feature store to look up features, and then we rank them with the ranking model. And this is all online infrastructure that you need to enable this retrieval and ranking infrastructure. And this is kind of what it looks like just from a kind of end-to-end sense. What we can actually do is we can deploy this, what we see in the middle, as a KServe model, as a set of steps in KServe. So you can actually have an inference graph in KServe that does what we're showing you here. Of course, you can also implement this in a microservice and make the microservice available. But basically, it's going to be a service that takes the user query in, goes to the feature store to enrich that with features about what the users just watched and their history. It'll compute the embedding, and that model will be hosted over KServe. So it'll send the request to KServe. It'll return with the embedding, and the embedding will send to OpenSearch. This is our embedding store to give us the candidates. And those 200 or 500 candidates, we're going to go back to the feature store to get more features for them, and we're going to rank them. So we're going to rank them with this ranking model. And the model again will be hosted in KServe, and then we can return the results to the user. So finally, then, when the user maybe has clicked on a video, that's the outcome, we'd like to push that outcome back into the feature store so that we're able to create new training data based on the predictions that we made and then the outcome of what the user actually clicked on. So at this point, I'm going to hand over to Javier, who'll just give you a feel for what the platform looks like with the new KServe capabilities in our user interface and with the new HSML library. So Javier, I'm going to stop sharing my screen. So I'll let you take over.
Hello.
We have some questions, but I think maybe we'll take them. Will I take them after or will I take them now? I'll take them now. So the first one is, you can start sharing your screen, Javier, while I take them.
Yeah, I will try to.
So Byron has, how is multi-model serving different from model mesh? It's a great question because model mesh is multi-model serving, but it's like you have one container. So there are some limits on even multi-model serving in KServe. There are limits, upper limits on the number of models you can deploy in a pod. And I think it's related to the number of IP addresses available. I think it's on the order of several hundred. Now, model mesh can serve thousands of models from a single server. So it's kind of an order of magnitude more scalable. Let's take the other questions after the demo. So you can go ahead there.
Yeah, I can start. So Hello, everyone. I will go through one of the examples that we have in our GitHub repository. You can also access through Hopsworks AI examples. And basically, we will see how to use HSFS to do some feature engineering and create feature groups, train data set, then train a model and serve it with HSML. So also at the same time, I will show the UI for the different parts. So basically, we can start first. We will need to import some libraries. You can go to the Python libraries section in the UI, and you can easily install a new library here using pip, conda, and so on, and check the version, or if you want to change one or so on. And then let me check because there is this bar. Yeah, okay. So then once you have the libraries that you need, you can start loading your data. You can use HSFS to do some to create some feature groups for your features. For that, you have, as Jim saw before, you need to import HSFS, create a connection to the Hopsworks feature store, and then from that you can start creating the feature groups using the data frames that you were previously built or obtained by after doing some feature engineering. And when you create these feature groups, you can go to the feature group section in the UI, and we see that we have here 2 feature groups. This one contains, in this case, for 5 features, the label, which is the final prediction, and for features for that are used as model input. In this case, this is the iris flower classification problem that we are mostly familiar with. And then after creating the feature groups, you can also create a training data set that will appear in the other sections, but we don't need to go into that for now. And once you have the training data set already prepared, you can use, for example, scikit-learn to create, to train a model on this data. And once we train the model that we have here, it will, in this case, it's in our iris KNN object. We can export it to our model registry using HSML. For that, all we need to do is to import HSML and basically specify where, in which path in the local system is this model store. And also you can specify the schemas for both the model inputs and also the output. And we can infer these schemas directly if you specify which data frames you use to train the model and which were the label. We can infer the schema from that. And also when you're creating the model, you can specify an input example, which is useful for quickly test your model and make some predictions. And probably if you have a more complex pipeline, you can run some tests just using this given input example. And after you have exported models to the model registry, you can go to the UI. Let's go here. I already trained several ones. Let's refresh. Yeah, 8 of them, 8 versions of the same classifier. We can see all the versions here on the side. If we click on one, we can see that it was trained with the scikit-learn framework. There are no deployments yet that are serving this model. We can see that the metric that we specified when we exported the model was 0.98 in this case of accuracy. And also we can have an overview of the schemas for the model inputs in this case, which the four features for this model, and then also for the prediction. And also we have here some code snippets if you want to start quickly and connect with the model registry, get your model by name, version in this case, and also how you can download the artifact with all the files that were in the path when you exported your model. So in this case, the artifact can contain the model, the pickle files, for example, of the model, but also you can include other files, like, for example, a pipeline object. If you are using scikit-learn and you want to perform some transformations here directly. And, or for example, in case of TensorFlow, you will have also the variables, weights, and so on. So after we created the model, we can continue here, and we can get which is the best model of these 8 versions that we have. And just to deploy the model, all we need to do is to call deploy, and it's already the deployment is already created but not started. And in this case, if you don't specify any parameters, we use default values for almost all the configuration that you can specify, which I will show later. And then also you can describe you can describe the deployment to see the configuration that is being considered in this case. So we can see the default values that were used for the deployment. So once you create you will deploy and you create the deployment, you could see it here. We see that the name of the deployment, which model was is the one that is served, the version of the artifact in this case, and the author and so on, the status. And we can even start it here, but let's continue. Then, so in this case, this was a simple deployment, which is just running the model. So in this case, in KServe, you don't need to specify predictor scripts or transformer scripts. If it's one of the frameworks that are supported, you can directly create serve these models. So this is the first case, which is the simplest one. But if we go for a bit more complex one, in which we want to deploy a predictor and transformer, all we have to do is specify a predictor script, which has to implement the class predict, and also there is 3 methods, which is predict, classify, and regress. And here, for example, we can use again HTML in the initialization method to create a connection, connect with the model registry, get the model and version that we are serving, download the artifact, and basically directly load the pickle file in this case. But as I said, here we could have also a pipeline object or more complex logic here. And then basically for the predict method, we just call predict in our model with the inputs that are that we are receiving here. And then in case of if you want to deploy also a transformer script to transform your model inputs before you make predictions with them, all you have to do is to implement the class transformer, which has a pre-process method and post-process method. And in this case, we can, as Jim mentioned before, we can create a connection with use HSFS to connect with the feature store, and then also get a feature view of the features that are involved that are related to this model. And then we basically can, in the pre-process method, we could just get the feature vectors directly from the on a feature store that then finally will be used to make the predictions. But in this case, since is the IDS flower classification problem, we don't need to add this extra logic here. So we'll just return the inputs, but this is an example. And then in case that we want to deploy this predictor script and transformer script, this is how you could do it. You could create a predictor configuration object in which you can specify which is the model server for the predictor, which can be a Python, TensorFlow, serving, and so on. A serving tool, which you can specify that you want to deploy it with KServe, and the predictor script, the path to the to this script. And then you have extra optional configuration, as I mentioned before, like for example, resources, how many cores, memory, GPU as well, a number of instances, and also if you want to log the inference requests into Kafka, you can also specify it here, specifying the topic, and more or less the same, almost the same for the transformer configuration. In this case, we don't have a model server, for example, but still you can specify the transformer script, also resources that will be allocated to the transformer, and the inference logger configuration in case you want to log the original request and also the ones these inputs have been transformed. So this, what it allows you is to have a more fine-grained inference logging in the whole process. So after that, we can just
I think we'll have to go quick on this, Javier, because we're at the top of the hour.
Yeah,
so we can skip to the end.
So basically, you can again call deploy, and you will see it here. The UI, yeah, start the deployment, and if you click on one of the, in this case, it's starting. This is how it looks like. You can see the models that are being served in this deployment with links that will redirect directly to the model view or model version view, which is the artifact version that we are using, the model server, and also links to the files if you want to download them directly, the predictor script, transformer script, or the whole artifact as a zip file. Also, you can see the endpoints to make inference requests, and again how the inputs for making predictions should look like, which is the scheme of these inputs, and which is the scheme of the prediction that you will get, and again some code snippets to make it easier to use or to start with.
All right.
Yeah, I think that's pretty much it.
Great.
Yeah.
Thanks, Javier. Okay, we have a few questions. I know we're out of time. Just right, it's just at the top of there right now. But we'll take the questions in the Q&A part. We've Yingding asks, can the model registry in Hopsworks also work with DVC? So HSML library that we showed here, it's a Python library. You can run it anywhere. Now I know DVC is a a data versioning control system. So it's not you would normally use it with the Python client. So that's fine. Okay, we have a question from an anonymous attendee. Usually service providers store data up to 3 years. So how do you store features for backtesting models and optimizing? Sorry, somebody did that. Okay, let's go back. So how do you store features for backtesting models and optimizing storage usage? For example, company has features that are relative in time, sales last month, sales last 2 months, 3 months. This way you will receive overlapping and duplicating use of data if they use snapshotting every week. Yeah, so I mean, of course, if regulatory reasons say you have to store through 3 years of data, you can. Now, what we can do, it's in our new version of our platform coming out. What we're able to do is delete training data sets and then recreate them exactly as they were from the feature store. So, for example, one of the things is that you have the feature groups themselves will collect data over time. And maybe you can clean up from 3 years ago. You can say, well, I'll remove all the data from 3 years ago, but they don't need it. But the training data sets that you create from the feature groups, and you don't have to create training data sets, you can get pandas data frames, but sometimes you do because your training data doesn't fit in memory. We'll have the capability to be able to recreate them at any point in time through using just the metadata for them. And then you can delete the actual data. So if you're doing hyperparameter tuning by creating many different training data sets with sets of features, you can go and delete them and then recreate them if you need to show something. So there's no magic wand for, if you have lots of different redundant features, there's no magic wand for getting rid of them. Another question from Byron: can the model registry keep track of changes in hyperparameters? So hyperparameters are related to experiments, and they will be stored typically in your experiment tracking system. So we have one in Hopsworks based on TensorBoard, but a lot of people use MLflow and weights and biases, and that's typically where the hyperparameters for your tuning would stay. What we can do is you can attach any metric you want with your model. So if you want to store your hyperparameters as part of that dict, with your Python with your model, you can do that. So you can see them straight up there if you want. If you used our platform for training, you could actually be able to click the experiment and see it as well. So I think we're out of time. We went a little bit over time, and I'm sorry for taking a couple of minutes of your extra time. But thanks for attending. And you can go to Hopsworks AI to get started, and you can install the open source version. And please reach out to us if you have questions or would like to try it out.
Thank you, Jim. Thank you, Javier. Just a reminder, we share here in the chat a link. We're gonna do a live coding Hopsworks open source tomorrow. So if you're interested to learn, join us tomorrow. Here's the link for you to register. Thanks, everyone. If you have any questions, let us know, and you'll be receiving a recording.
Good, everyone.
Bye.
Bye. Bye.